Hello students, welcome to the world of stereochemistry. Discover the 3D magic of molecules. Learn how the arrangement of atoms changes everything. Explore why shape and structure matter in chemistry, biology, and daily life. Stereochemistry is important because the 3D arrangement of atoms in a molecule affects how it works in the body and in chemical reactions. For example, one form of a drug might heal, while another could harm. It also helps us create better materials, safer medicines, and eco-friendly chemicals. Understanding stereochemistry helps us explain how molecules behave and interact in everyday life. Stereochemistry studies the three-dimensional shapes of molecules and their impact on reactivity. It involves understanding the spatial arrangements of atoms in molecules. Isomerism involves compounds with the same molecular formula but different structures or properties. Structural isomers differ in connectivity, while stereoisomers differ in spatial arrangement. Students, this flowchart helps determine the type of isomerism by analyzing molecular structure and connectivity. It distinguishes between constitutional isomers and stereoisomers. Constitutional isomerism involves compounds with the same molecular formula but different connectivity of atoms. Examples include ortho-dichlorobenzene and para-dichlorobenzene. Structural or constitutional isomers have the same molecular formula but different atom arrangements. They include chain, positional, functional, metamerism, and tautomerism isomers. Functional isomerism occurs when compounds have the same chemical formula but different functional groups. Examples include propanal and propanone. Positional isomerism involves compounds with the same chemical formula but different positions of functional groups. Examples include 1-chloropropane and 2-chloropropane. Chain isomerism occurs when compounds have the same chemical formula but different carbon chain structures. Examples include N-butane and isobutane. Metamerism isomerism involves compounds with the same chemical formula but different distributions of alkyl groups around a central atom. Examples include methylpropanoate and ethyl ethanoate. Tautomerism refers to isomers that differ in the position of protons and electrons, often existing in equilibrium. An example is the keto-enol tautomerism of acetone. Stereoisomerism involves compounds with the same molecular formula but different spatial arrangements of atoms. This includes geometric and optical isomers. Geometric isomers differ in spatial arrangement around a double bond, while optical isomers are non-superimposable mirror images. Examples include cis-trans isomers and enantiomers. Correctly drawing stereochemistry involves using dashed lines for bonds going away and solid lines for bonds coming towards the viewer. This helps in visualizing molecular structures. Preferred drawing conventions in stereochemistry ensure clarity and accuracy in representing molecular structures. Incorrect methods can lead to misunderstandings. Perspective and sawhorse projection formulas are used to represent three-dimensional structures of molecules. These conventions help in visualizing stereoisomers. Newman projection formula helps visualize the spatial arrangement of atoms in a molecule by looking down the bond axis. It uses hashes and wedges to indicate bond directions. Fisher projection formula represents three-dimensional molecules in 2 dimensions, with the main carbon chain in the vertical plane. It simplifies the visualization of complex molecules. Converting between Fisher and sawhorse projections helps in understanding the spatial arrangement of molecules. This is crucial for analyzing stereochemistry. In stereochemistry, drawing conventions like the staggered and eclipsed Newman projections and the Fisher projection help visualize molecular structures in 3 dimensions. Optical isomers can rotate the plane of polarized light, a phenomenon known as optical isomerism. This occurs when light passes through a polarizing filter, converting it to plane polarized light. A polarimeter measures how plane polarized light interacts with chiral molecules. This interaction helps determine the optical activity of a substance. Optical activity refers to a compound's ability to rotate plane polarized light either clockwise or counterclockwise, indicating its chiral nature. Specific rotation quantifies the optical activity of a chiral substance, measured in a 1 decimeter tube at a specific concentration. It is symbolized by alpha d. Dextro-rotatory compounds rotate plane polarized light to the right, while levo-rotatory compounds rotate it to the left. These properties are denoted by d, or, plus, and L, or, respectively. An asymmetric carbon atom, or chiral center, is attached to 4 different atoms or groups. The number of stereoisomers is 2n, where n is the number of asymmetric carbon atoms. Chiral molecules have 4 different groups attached to a carbon atom, making them non-superimposable on their mirror images. Achiral molecules do not have this property. Students, please note that chiral molecules are not superimposable on their mirror images and can rotate plane polarized light in opposite directions, a property known as racemic mixture. Achiral molecules can be superimposed on their mirror images and do not rotate plane polarized light. They have a plane or center of symmetry. The presence or absence of a plane of symmetry determines if an object is chiral or achiral. Chiral objects lack a plane of symmetry, while achiral objects have one. A center of symmetry in a molecule means that identical atoms or groups are equidistant from a central point, making the molecule achiral and optically inactive. An axis of symmetry involves rotating a molecule around an axis to produce an identical arrangement. This can be a simple or alternating axis of symmetry. An alternating axis of symmetry involves rotation followed by reflection through a plane perpendicular to the axis, creating a symmetrical arrangement. Further, enantiomers are stereoisomers that are non-superimposable mirror images of each other. This relationship is called enantiomerism. Diastereomers are stereoisomers that are not mirror images of each other. This phenomenon is known as diastereomerism. This brings us to the end of our presentation. I hope you found it helpful and enjoyable. If you liked the video, please give it a thumbs up and share it with others. Take care and see you in the next video. Goodbye.